Okay, so hello everyone. Hope am I audible? So I am Subrata Samanta. I am one of the TA for the thermal physics course that is taken by Professor Devmalla Banerjee in this semester. So for today I will discuss some basic concept of the thermodynamic course because the NSEM exams is approaching. Okay, and and tomorrow I will solve the assignment 12 problems. So today I will recap the things that we have learned so far. So, okay, and uh, some extra problems I will solve at the end. Okay, so let's start with a few basic concept, that is basically, so you so far you have learned that the first law of thermodynamics and the second law of thermodynamics, right? But there is also a third law of thermodynamics, right? But so this third law of thermodynamics I will discuss a little bit, and then I will move into the problems. Okay, solve some problems. Okay, so first let me share my screen, and so if you have any questions you can ask directly. Okay, and unmute yourselves. Okay, and ask your questions, or you can also raise your questions in the discussion forums. Okay, so don't hesitate to ask your questions. Okay, and all the sessions are recorded. Okay, it will be uploaded on the YouTubes. Okay, and the links here to you all. Okay, so okay, so let's first share my screen. Yeah, hope my screen is visible. Okay, right, all right. So so far you have learned that the first law of thermodynamics and the second law of thermodynamics, right? But so what is the third law of thermodynamics? Okay, but before so also we have learned, so first we learned that the third law of thermodynamics. Okay, so third law of thermodynamics, I will discuss a little bit about this. And the second, so you know you have studies that the thermodynamics of various other kind of systems, right? So basically so you have studies that the thermodynamics of other kind of systems, thermodynamics of other kind of system, right? So what are this systems is basically rod, okay, bubbles and magnetisms, right? The magnets, so rod, bubbles, right, magnets. Okay, so basically your key example is that, so you know that there is some ideal gas, right? Thermodynamics of ideal gas, right? And how is to generalize to other kind of systems. Okay, basically thermodynamics of uh, of a magnet system. So right, so you know we have studied so far this kind of things. Okay, so basically use ideal gas as in basic examples. Okay, and you developed the thermodynamics of other kind of systems. Okay, so today we will study the thermodynamics of black body radiations, right? So this is very one of the good things, that we study the thermodynamics of black body radiations. Thermodynamics, and this is important. Okay, so thermodynamics of black body radiations. Okay, so use the same I think idea. So if you know that, so basically your so your ideal gas, right? So in principles thermodynamics can apply to other types of systems. So in principles thermodynamics, okay, can be applied, okay, can be applied to other type of systems except ideal, apart from the ideal gas. Okay, so other type of system, okay, apart from ideal gas, okay, apart from ideal gas. So ideal gas is a key example. So you use these properties, okay, it can also apply to other kind of systems. So in general, your work done dw, okay, so this is your I think differentials in work done, okay, dw, that is basically your capital X, okay, small x. So in the previous class we have discussed, right? So at capital X, so this is basically generalized forces, right? So generalized force, okay, and your small x, your generalized displacement, right? Okay, and it depends on, suppose your ideal gas, it's basically pdv, right? Okay, and for rod system is basically fdl, right? So your f is tension and l is length, okay. So for a system of rod, so this is basically fdl. So we will study this, and mainly we will study the thermodynamics of a black body radiation. So what is this quantity for black body radiation, so we will see, okay, in a few minutes. So these three things we will discuss, and then I will solve some problems at the end, okay. So that is basically the structure of the class today. And okay, so we start with in the third law of thermodynamics, okay. So this one, okay. So okay, so first I will discuss third law of thermodynamics. First of all, so why we need this third law of thermodynamics, right? So you know that the first law of thermodynamics and have a second law of thermodynamics, okay. So first law we have studies, right? First law of thermodynamics and second law of okay, so second law of thermodynamics, right? and and we have also seen that the second law of thermodynamics have various form, right? Basically the Kelvin statements, okay, Clausius statements, okay. So basically so have various forms, right? And that basically the concept to the entropy, that is important. So all these forms, okay, basically to the concept of entropy. So basically to the concept of entropy, that is basically the second law of thermodynamics. Similarly, the third law of thermodynamics also have various forms, right? So Nernst theorems and Nernst statements, Planck statements, okay, and also Simon statements. So there are three statements for the third law of thermodynamics, okay. So third law of thermodynamics also have various forms, okay? Also have various forms, okay? Also have various forms, okay? So now the thing is that why we need third law of thermodynamics, and what the thermodynamics tells about, right? So if you know entropy, let's start with the entropy, right? So you know entropy of an isolated systems always increase with times or fixed, right? So the second law of thermodynamics tells you that the entropy, okay, this concept to the entropy, that is the second law of thermodynamics, and the second law of thermodynamics tells about that the entropy of an isolated system, of an isolated system, okay, always increase with time or fixed, okay. So always increase with time, okay, or fixed. So the delta S, the change in entropy delta S is basically greater than equals to 0. Okay, so if sorry, so if it is okay, so if it is 0, then there is no change in entropy, so entropy is fixed or is changing with time. It's positive, right? So greater than 0, that means it's positive, so always increasing with times, right? So but you would notice that you always talk about the change in entropy, not the entropy, the absolute values of the entropy, right? So but what the value does the entropy of a system take, and how can we measure it? So the question is that, but what does what value does what value, okay, does the entropy of a system take, right? Entropy of a system take, right? And how can we measure it? Okay, and how can you measure? Okay, and how can you measure? Okay, so this is the questions. Okay, that is basically interesting. So one way of measuring the entropy of a system is to measure its heat capacity. So basically there is one way to measure the entropy. So one way of measuring entropy, okay, of a system is to measure its heat capacity. Okay, so is to measure its okay, is to measure its capacity, right? Because the heat capacity, let's say Cp, okay, so your Cp is basically T delta S over del T at constant temperatures, sorry, at constant pressure. This is your Cp, right? And we can obtain entropy by integrating this. Okay, so we can obtain entropy. So the entropy is basically, so once you integrate this S, okay, that is basically you integrate Cp over T and then dt, right? Okay, right, but this is an indefinite integral, right? So we have to worry about the constant of the integration. So now this is an indefinite integral. Okay, so indefinite integral. Okay, so you have to worry about the constant of integrations. Okay, so we have to about constant of integrations, right? So you have to worry about the constant of integration, right? Okay, so basically let's say we can write that S at some temperature T is basically S at T naught plus T naught to T and then Cp over T dt. Okay, so basically if we plot, let's say Cp over T, okay, versus temperature, okay, and let's say curve this. Okay, so definite integral means that area under the curve, right? So basically if we draw a two lines, okay, and the area under the curve is basically, let's say, T naught to T, okay, that is T naught to T Cp over T Fx times dt dx, right? This is the area under the curve, and that gives you, so because your curve is this, So this is your curve, right? So therefore, which is equals to St minus St naught, right? So now the question is what is St naught, right? So this is St basically measure the entropy at temperature T. So this is the measure the entropy at temperature T, and this T naught, okay, basically the entropy at some different temperature T naught. Okay, so entropy at some different temperature T naught. Okay, right. So to know that what is St naught, right? So therefore, if you calculate the area under the curve, that gives you the entropy difference St minus St naught, right? So you have to know what is St naught, right? So you are only able to learn about the change in entropy, that is basically your area under the curve. Okay, we do not know what is the absolute values of the entropy. Okay, so the conclusion is that so we are only able to learn about, so we are only able to learn about the change in entropy, right? Because system, if you want from T naught to T, okay, then what is the change in entropy? Okay, so we are not able to obtain an absolute measurement of entropy itself. And the third law of thermodynamics gives you an additional information. Basically, what is the entropy at absolute zero temperatures, right? Absolute zero temperatures. Okay. So we are only able to learn about the change in entropy, and when you warm the systems, okay, from T naught to T naught T. So if you warm, okay, the system T naught to T, okay, so your T naught temperature to T temperatures, okay, and we are only able to obtain the absolute measurements of the entropy. Okay, sorry, we are calculate the change in entropy, not the absolute. So we are not able to obtain the absolute. So we are not able to obtain an absolute measurement of entropy. So here the third law basically gives you an additional information. Okay, so now the third law of thermodynamics, okay, gives us additional information, right? Because it provides a value, okay, for the entropy at absolute zero temperatures. Okay. Because it provides, so what does this what is the additional information? Because it provides the values of entropy, provide the value of entropy okay, at one particular temperatures, basically absolute zero temperature. So the value of entropy at one particular temperature So this is not a non-zero temperature, it's absolute zero temperature. So this particular temperature is basically absolute zero temperature. So absolute zero temperatures. Okay. So it's absolute zero temperature. So what is the values of the entropy at absolute zero temperatures? That information gives you the third law of thermodynamics. Sorry. Okay. So now, what is the value of the entropy at absolute zero temperature? Sorry. So there is a statements that is called three statements. I also discussed that there is also various form of third law of thermodynamics, okay, similar to the second law of thermodynamics. Okay, so I will discuss one by one. So first one is that the Nernst statements. Okay. Okay. So, so this statement is that the near absolute zero temperature. Okay. All reactions in the systems. Okay. It's internal equilibrium. Right. So near absolute zero temperature. So near absolute zero temperature, okay, all reaction in a system, all reaction in a system in internal equilibrium, internal equilibrium, okay, in internal equilibrium. So all reaction in a systems in internal equilibrium take place, okay, with no change in entropy, because it's in internal equilibriums, okay, and the entropy is basically your ergodicity in a systems. But if it is internal equilibriums with no change in entropy, with no change in entropy, right? So that basically your S is tends to 0 or delta S is tends to 0 as T tends to 0, right? So your delta S tends to 0 as T tends to 0. Okay. So the second one is basically the Planck statement. Okay. So Planck statement. So the entropy of all system in internal equilibrium. Okay. So entropy, the Planck statement is that the entropy of all system in internal equilibrium is the if in internal equilibrium, okay, is the same. So the entropy of all systems in internal equilibrium is the same, okay, at absolute zero temperatures, okay, at absolute zero temperature, okay, and may be taken to be 0, and may be taken to be 0. Right. So the entropy, now this is talking about the absolute values of the entropy, right? So the entropy of all the systems, okay, in internal equilibrium is the same at absolute 0 temperatures and may be taken to be 0. So that means S is tends to 0 as T tends to 0. Okay. So this is the same. So S is tends to 0 as T tends to 0. Right. So Planck actually made his statements, okay, only about the perfect crystal. Okay, I think Planck, so I wrote this down. So the Planck, okay, actually made his statement, okay, these statements only about perfect crystal, only about perfect crystal, okay, that the entropy of all the system basically type crystal type system, okay, are internal equilibriums at absolute 0 and may be taken to be 0. Okay, the entropy is 0 as T tends to 0, but it believes to be true for any kind of systems. Okay, but it believes to be true, okay, for any kind of system. Okay, and the last one is the Simon statements. Okay. So okay, so the Nernst statements, Planck statements, and the Simon statements. Sorry. So the last one is the okay. So Simon statements, and that, so this basically the contributions to the entropy of a system. Okay, the statement is that the contribution to the entropy of a system, right, by each aspect of the systems, okay, by each, so this one is very crucial, each aspect of the system, so each aspect of the system, okay, which is in internal thermodynamic equilibrium. So each aspect of the system which is in internal thermodynamic equilibrium, internal thermodynamic equilibrium, okay, tends to 0 as T tends to 0, tends to 0 as T tends to 0, right. Right, so this one is tends to 0, sorry, so this one is tends to 0 as T tends to 0, but the difference is that the Simon statements is the basically tells you that the contributions to the entropy of a systems, okay, by each aspect of the systems which is in internal thermodynamic equilibrium tends to 0. So each aspect of the system is important, okay, because yes, so because it focus on a particular aspect of interest, okay, so because So because it focus on a particular aspect of interest, okay, knowing that its entropy tends to 0 as t tends to 0, and we would, do not worry about or ignoring the aspects, other kind of aspect of the system. So basically it focus on a particular aspects of interest, okay, knowing that, so in that aspect of interest, okay, knowing that the entropy tends to 0 as t tends to 0, so knowing that its entropy tends to 0 as t tends to 0, okay, and ignoring the aspect that we do not care about, okay, and ignoring the aspects, okay, and ignoring the other kind of aspects, other kind of aspects, okay, we do not worry about, we do not care about. So and ignoring the other kind of aspects we do not care about, okay. Right. So now if we say that as t tends to 0, if the entropy tends to 0, okay, what are the other properties? And so I am saying that let's say consider a Carnot engines, okay. So let's consider a Carnot engines, okay, and that is operate between two reservoirs, okay. So let's draw a diagrams, okay. So let's say this one is TL, sorry, TH, okay, the high reservoirs, high temperature reservoirs, and this one is TL, the low temperature reservoirs, okay, and the Carnot engine operate between these two. So it's a work done, okay, and the heat flow QH, QL, and this one is a work done, right, W, okay, and that's basically your Carnot engine. So suppose your TL tends to 0, right, and you know the efficiency is eta, okay, so this is basically efficiency eta is 1 minus TL over TH. So if TL tends to 0, okay, then your eta tends to 1, right. So if TL tends to 0, then eta tends to 1, right. So that means at absolute 0 temperatures your efficiency is 1. So complete conversions of heat into work, right. So at absolute 0 temperatures the perfect conversions of heat into work, right. But there is a problem, right. So what is the problem? Yeah, so the problem is that basically it violates the Kelvin statements of second law of thermodynamics, right. So the second law of thermodynamics, okay, tells about that the complete conversions of heat into work is not possible. So that means efficiency cannot be 1, okay. But if you see that if you put TL tends to 0, okay, that means it tends to 1, right. This is violate the violation of Kelvin statements of second law of thermodynamics. Statement of second law of thermodynamics, right? Okay. So what is the fallacy here? Okay. The fallacy is that so there is some difficulties. Okay. So what are the difficulties? So it is not clear. Okay. How can you perform? Okay. So how can you perform at isothermal process? Okay. At absolute zero temperature. So how can you perform isothermal process at absolute zero temperatures? Right. Because so it is not clear. So how the question is that how can you or how you can perform okay isothermal process okay, at absolute zero temperature. So at absolute okay at absolute zero temperature. How you can perform the isothermal process at absolute zero temperatures? Okay, because once the system is at absolute zero, right, it is not possible to get it to change the state, its thermodynamic steps, without warming it. Okay. So why I'm asking this? Because once a system okay is at absolute zero, okay, it is not possible to get it to change okay its thermodynamic states without warming it. Okay, its thermodynamic state without warming it. Okay, so that is it. So at absolute zero temperatures you cannot change the state of thermodynamic states of a system, right? Then how can you perform the isothermal process okay, at absolute zero temperature? So this kind of things subtleties. Okay, so we believe so therefore we believe that okay the third law of thermodynamics okay is indeed a separate uh, postulates okay which is independent of the second law of thermodynamics. Okay. So third law okay is indeed a separate postulate okay. So indeed a separate postulate which is independent of the second law, which is of second law. Okay, so it's independent of second law of thermodynamics. Okay, and also it is impossible to achieve, or it is impossible to achieve at, or it is impossible, so it is also it is impossible to cool. So it is impossible to cool to T equals to 0 in a finite number of step. Okay. In a finite number of step. Okay. Right. So this is one thing is important, that you cannot achieve T equals to 0 temperatures, okay, at a finite number of steps. Okay, so now what are the consequences of third law of thermodynamics? Okay, so what are the consequences of third law of thermodynamics then? So the consequence of third law of thermodynamics, okay. So the first consequence is that the specific heat tends to 0 at as T tends to 0, or specific heat C tends to 0 as T tends to 0, because entropy tends to 0. Okay, and your C basically the derivative of entropy, right? So because entropy tends to 0 as T tends to 0, okay, this is basically your Planck statements. Okay. And your Cp, the specific heat at constant pressure, basically T, the change in entropy del S del T at constant pressure, so this tends to 0. Okay, so Cv also tends to 0, and the specific heat tends to 0. So, and the second one is that the thermal expansion stop. So thermal expansion, okay, stops, right? So thermal expansion is, let's beta P, right? So which is basically 1 over V del V del T at constant pressures, which is tends to 0, right? Because if you use the Maxwell equations, okay, so the Maxwell equations is del V del T at constant P is equals to minus del S del P at constant T, right? So because S is the tends to 0 as T tends to 0, so del S del P at constant T tends to 0 as T tends to 0, so that's why this beta P also tends to 0, right? So that means the thermal expansion stops. Okay, at this temperature. So the thermal expansion stops. Okay. Okay. So and the third one is that no gas remains ideal, because you know that the for ideal gas, so for ideal gas you know that the Cp minus Cv, the specific heat at constant pressure minus specific heat at constant volume, is basically R, right? So 1 mole of ideal gas, so this is R, right? It's fixed. Okay, and R is basically your universal gas constant. So this is your universal gas constant, right? And that is fixed. Okay, so now at t tends to 0, so as t tends to 0, your Cp tends to 0 and Cv tends to 0, right? As t tends to 0, this implies that Cp minus Cv, right, tends to 0. Okay, so that means this property is not hold, that Cp minus Cv is fixed. Okay, basically it tends to 0, right? So that means the no gas ideals remains ideal at t tends to 0, right? So no gas no gas remains ideal as t tends to 0. Okay, okay, so that is things. And so okay, so that's all about the very brief introductions of the third law of thermodynamics and some consequences of this. Okay, so the next I will move into the thermodynamics of black body radiations. Okay, and then I will solve some problems. So yeah, so if you have any questions, you can raise your questions in the discussions forum. Okay. Okay, so then I will move to the discussions of the thermodynamics of black body radiations. Okay, so let's start with the thermodynamics of black body radiations. Right. So you know that the Helmholtz energy for black body radiation. Okay, so we start from this. So Helmholtz energy for black body radiations that derived from some statistical mechanics, but I'm not going into this. So we are basically starting the thermodynamics. So we start with from Helmholtz energy, right? So Helmholtz energy sorry. So Helmholtz free energy, that is basically F, okay, it basically H plus PV, okay, so it's enthalpy and then definition. So it's minus 4 sigma over 3c times V T to the power 4, right? So T is the temperature and V is the volume, cavity volume, okay, and sigma is the Stefan constants, okay. So and C is the speed of light, okay. So sigma is the Stefan's Boltzmann constants, Boltzmann constant, okay, and your C is the speed of light, right? And if V is the cavity volume, T is the temperature, that is the info, right? And calculate the corresponding equations of state, okay. So once the Helmholtz energy provided, okay, you can compute the equations of states, okay. So the question is that calculate the corresponding equations of state, okay. So if P V T and the functions of f p v t equals to 0, that is the equations of states, and the variables is p v and t. Okay. So how do we compute? So Helmholtz free energy is given, okay. So start from this, okay. Right? So you know that df basically minus sdt minus pdv, right? Okay, and your entropy is equals to minus del f over del t at constant v, right? So from the partial differential equation, so you know this, okay? Because you can write df is, if f is a functions of v and t, so then df is the total derivatives is basically del f the partial one over del v at constant t dv plus del f over del t at constant v then dt, right? And compare with this equations and this, right? So s is this, s becomes this. So then what is the values of the s? Because we know the f is given, right? We know f, okay. So plug the values and take one more derivatives with respect to t. So this is basically 16. So minus minus become plus. So 16 sigma over 3c v t cube, okay. So which implies that your entropy is proportional to t cube. That is one of the key result, okay. So that entropy is proportional to t to the power cube, okay. Similarly, if we compute the internal energy, So another thing is that the entropy, second one is the internal energy. Okay, so internal energy E is basically your F plus Ts, right? And okay, so now you know that F plus Ts, so that's basically tells you that F, right, and minus, so T times S, right? So S is basically, so if you just multiply it with this, so T times your S is 16 sigma over 3c Vt cube, right? 16 sigma over 3c Vt cube, right? So this is basically 4f, right? So f minus 4 times f, right? Because f is 4 sigma over 3c, right, with a minus sign. So therefore this is basically your minus 3f. Okay. So E equals to minus 3f. So that means the internal energy proportional to T to the power 4. Okay. So it's not T to the power cube. The entropy is proportional to T to the power cube. So your internal energy is proportional to T to the power 4. Right. And also the specific heat. Now the third one is the specific heat. So specific heat, right? So this is basically a CV, and that daily del T at constant volume V, right? So now if you know that E is proportional to T to the power 4, so this becomes your CV is E is minus 3f, so f is already minus, so yeah, so this becomes 4, and yeah, so this is basically proportional to T to the power cube, right? So entropy and specific heats are same. Okay, it's proportional to T to the power cube. Okay, so now the pressure, right? So pressure, so once you know the free energy, okay, you can compute the pressure easily. Okay, so this pressure is from these equations. Okay, your pressure, so this is pressure, right, and this is the same, sorry, this one. So del F del V at constant temperatures, okay, that gives you the pressure, right? Okay, so pressure P equals to minus del F del V at constant temperatures, right? So now if you know that F is basically your minus 4 sigma over 3c Vt cube, so take on more derivative with respect to V, so it's basically 4 sigma over 3c times T to the power 4, right? Okay, and if you multiply it with V, so PV equals to, so this implies that, so P times V is equals to 4 sigma over 3c V T to the power 4, right? So this is nothing but the minus F, okay, and minus F is basically, and we know that E equals to minus 3f, right? So E equals to minus 3f, so F equals to 1 over 3e, right? So basically 1 over 3e, right? and the equations of state for the photon gas, then the black body radiation is PV equals to 1/3E, right? So this is basically the equations of state for photon gas. Equations of state for black body radiations or photon gas. Okay. So this is basically relativistic gas. Okay. For ideal gas, okay, this is a classical gas. Okay. The PV is equals to 2/3 E, right? Okay, and if we plug this, the E equals to 3/2 kVt, then this becomes PV equals to N kVt. Okay. So N is the number of moles. So PV equals to kVt, and for N mole gas is basically N kVt. Okay. Right? Okay. So you can also write the equations of state in this form, that PV equals to 1/3 E. That is basically for photon gas. Okay. And we know that how entropy and the specific heats, okay, vary with temperatures for photon gas. Okay. So the next thing is that, so once you know the pressure, right, because the pressure is uniquely determined by the temperatures only, right? So basically the pressures, the form of pressure, so if you closely look into this, the pressure P, okay, is 4 sigma over 3 c t to the power 4, right? So 4 sigma over 3 c t to the power 4, right? So therefore the pressure is uniquely determined. So therefore the pressure is uniquely determined by the temperature only. Okay, so it's uniquely determined by the temperature. So this is important because in these expressions only the T is the variables. Okay, sigma and C are constants. Okay? So sigma is the Stephen Boltzmann constants and C is the speed of light, so it's also constant. Okay? And only the variable is the T. And therefore the P and T are not really independent. So since you know that the DE equals to the second one is the DE equals to TDS, so one of the relations is minus PdV, right? Basically E is the functions of S and V. So E is the functions of S and V. Okay, and the Helmholtz free energy F, okay, is a functions of T and V. So for Lagrange multiplier is basically E minus Ts, right? Because E is a functions of S and V, and I have to convert a function or to construct a functions. Okay, that is basically functions of T and V. So use the Lagrange multiplier, so E minus Ts. And you have to convert the Gibbs free energy G is Pt, okay, then prefixed and then changes P. This is basically E minus Ts plus PV. Okay, so this is basically your Gibbs free energy. So this G is Gibbs free energy. Okay, so this F is the Helmholtz free energy, okay, I already told, okay, and the G is the Gibbs free energy. Okay. So therefore it's a, so what is the values of G for photon gas? Okay, so it is easily to calculate, okay, this. So for photon gas, G equals to, so what is the values of E? So E is basically, so E minus Ts is F, okay, and plus, so P is 4 sigma over 3C T to the power 4 times V, and that is nothing but the minus F, right? So it's F minus F, right? So it's 0. Okay, so the Gibbs free energy, it vanishes for the photon gas, right? Okay, but during the class, you also know that the G, the Gibbs free energy, also can be written as mu times N, right? Okay. So, so basically G equals to 0 for photon gas. Okay, and we know that G equals to mu times N. Okay, where N, mu is the chemical potential. So where mu is the chemical potential, right? And N is the number of photon. The number of photon, which is obviously not equals to 0. So that means mu equals to 0, right? So G equals to 0 implies that mu equals to 0. Right? So the chemical potential, okay, for the photon gas vanishes, right? A 0, right? So mu equals to 0. Okay. Okay, so now I have to move further. Then what about the entropy? So you know that entropy is basically, let's say for adiabatic process, okay, entropy is constant, right? So for adiabatic process, for adiabatic process, your delta S is 0. That means S is constant, right? Okay. And you know that the for photon gas, so photon gas, let's say for photon gas, we know that S is basically 16 sigma over 3C VT cube, right? And for adiabatic process, so your S is constant, right? So that means, and sigma C are also constants, because this is the Stefan Boltzmann constants, and the speed of light is also constant. So VT cube is constant, right? So adiabatic process, okay, implies that VT cube equals to constant, right? And you know that the adiabatic process is basically PV to the power gamma equals to constant, right? So if we just compare with this, so what is the values of gamma then? Okay, so we know that the adiabatic process is PV to the power gamma equals to constant. Okay, so it implies that T V to the power gamma minus 1 equals to constant. Okay, so if you compare with these two equations, that T V to the power gamma minus 1 and V T cube equals to constants. So basically, yeah, so 1 over gamma minus 1 is equals to 3, right? So gamma minus 1 is 1 over 3, gamma equals to 1 over 3, 4 over 3, right? So gamma equals to 4 over 3. So for photon gas or the relativistic gas, gamma is not equals to Cp over Cv, right? So this is not equals to, so the gamma is not equals to Cp over Cv. Okay, because this is not equals to for photon gas, basically for relativistic gas. So this is true for only non-relativistic gas. Okay, so gamma equals to Cp over 3 Cv, true, okay, for non-relativistic gas. Okay, non-relativistic gases. So you can also calculate the work done for adiabatic expenses, right? So you can also calculate work done. So calculate the work done for adiabatic expenses. Okay, so let's change the color. Okay, so how to calculate the work done for this adiabatic expenses? We know that for adiabatic process, the W is equals to minus initial volume Vi to Vf PdV. Okay, so this is basically Pi Vi minus Pf Vf over gamma minus 1. Okay, and we know that the PV equals to 1/3 for photon gas, so 1/3 Ei minus 1/3 Ef, okay, over gamma minus 1 is basically 4 over 3 minus 1. So that is basically 1/3. So W is basically Ei minus Ef. Okay, so change in energy. Right. So the energy is necessary to produce the expansions, okay, is extracted from the internal energy of the radiation. So therefore energy okay, so the energy necessary to produce the expansions okay, so the energy necessary to produce the expansion is extracted from the internal energy of the radiations. Okay. Okay, so far you have any questions? Okay, so then I will solve some problems. Okay, sample problems. So suppose the questions let's the question is that what are the adiabatic invariant quantities for the photon gas? Okay, so what are the adiabatic invariant quantities so adiabatic invariant quantities, okay, for the photon gas? Okay, okay, so we just discuss that the for adiabatic process the entropy is basically constant, so that means VT cube equals to constant, right? So that is one of the invariant quantity, so that entropy is constant, right? So S equals to constant, which implies that VT cube equals to constant, right? And which also implies that this is adiabatic invariance, right? Now if you know that V is basically is volume, right? And L cube, right? So that is basically lambda cube wavelength, right? And lambda is basically 1 over frequency, so 1 over nu cube, right? So this implies that nu cube V, sorry, nu cube V, right? So nu cube V, right? So this nu cube and V, so this nu cube V equals to also constant. So that means V cube T is an adiabatic invariant quantity, but nu cube V also an adiabatic invariant quantity. Okay, this is also adiabatic invariant. Right, so this is also adiabatic invariant. Okay, so now the second problem. Okay, so the second question is that how much heat is required to raise the temperature of 1000 grams of nitrogen, 1000 grams of nitrogen, okay, from minus 20 degrees centigrade to 100 degrees centigrade, okay, at constant pressure, at constant pressure, right? Okay, so this is one part. Okay, the second part is that how much has the internal energy of the nitrogen increased in the above process, how much has the internal energy okay of the nitrogen increased okay, and the third point is that how much external work was done, okay, how much external work was done, okay, right? So there's three problems. So three parts, okay. Okay, how to solve this problem? Okay, so in the first case is the delta Q, right? So you have to calculate the heat is required to raise the temperatures from 1000 grams of nitrogen, okay, from minus 20 degrees centigrade to 100 degrees centigrade, and heat is required, how much heat is required. So delta Q, so basically part A, okay, so delta Q, so that is basically N times Cp at constant pressure, right? So Cp, the associated specific heat is basically the specific heat at constant pressure, Cp times delta T, right? So change in temperature. So okay, so now the Cv and the specific heat is given. So Cv is given 5 calorie, right, per mole degree centigrade, and R is 2 calorie per mole degree centigrade, okay. So therefore what is the values of Cp then? So you know Cp minus Cv is basically R. So Cp is 5 plus 2, 7 calorie per mole degree centigrade, right? So and N is basically number of mole. Okay, so 1000 gram of nitrogen equals to, so 1000 over 28 gram basically equals to 1 mole, right? So 28 gram of nitrogen equals to 1 mole, so 1000 gram is basically 1000 over 28, this is basically number of moles, times your Cp is 7. Okay, and this is calorie per mole per degree centigrade, and your delta T is change in temperatures. Okay, also in the degree centigrade. So it's basically 100 times 20, so 100 minus 20, right? So this is basically 120, so 1000 over 28 times 7 times 120, right? So which is basically 4 and 4 30, right? So it's basically 3 times 10 to the power 4 calorie, right? So 3 times 10 to the power 4 calorie. Okay, consider nitrogen gas. So here, so when I use this, so Cp minus Cv equals to R. So consider, let's say assume, okay, nitrogen gas, nitrogen gas, okay, as an ideal gas. Okay. Okay, so this is your delta Q. Okay, so 3 times 10 to the power 4 calorie. Now the second part, basically you have to calculate how much has the internal energy of the nitrogen increased, right? So this is your second part. So then how to calculate this? So internal energy, right? So this is basically delta U. Okay. And similarly delta U is basically NCV delta T. Okay, that is related to your CV. Okay, and this is exactly same. So exactly same procedure. So N is basically your 1000 over 28 times your CV in this case is given. So it's 5 calorie per mole. So 5. Okay, times your delta T is 120 is calorie. So again you have 5. So in this case, yeah, so you have to calculate this. Okay. Right. So now what the third part, so part 3 is basically how much external work was done. Okay, so external work is basically, so now I have to use the first law of thermodynamics, right? So the first law of thermodynamics tells you that delta U, it's, so U is first law of thermodynamics. So delta U equals to delta Q plus delta W, right? So for delta W equals to delta U minus delta Q, right? You have calculated delta U. So delta U is basically 1000 over 28 times 5, and other one is 7. So 5 minus 7 times 120. calorie. So this one is negative, so minus 1000 over 28 times 2 times 120 calorie, right? Okay, so delta W is negative, right? So that implies that this is external work, right? So the delta W is negative, so now I am using here this plus sign, right? So plus delta W, and the delta W, it gives negative, so that means it's the external work. Okay, this means external work. Okay, this is the external work. Okay, so let's do one more problem. So let's say two systems. Okay, so system A, okay, the specific heat is C1, and the system B, okay, the specific heat is C2. So this is basically system A, and this one is system B, and system A has temperature T1, system B temperature T2. Okay, now if you connect, okay, thermally connected these two, okay, and your final temperature is TF. So TF is the final temperature, okay, and T1 is the temperature of the system A, temperature of system A, and T2 is the temperature of system B. You have to calculate, right? The temperature of system B, but you have to calculate this. Right? So what is the values of T2? So assume that the total energy of the combined system is conserved. So, so to assume that the total energy of the combined system, okay, and so connect system A and system B, then the final temperature TF, and assume that the total energy of the combined system is conserved. Okay, okay, how to solve this problem? Okay, so total energy conserved, that means your delta key is same, right? Right? So delta Q, okay, so heat transfer is basically N times C, the specific heat, times delta T, right? So the first systems is basically minus C1 for 1 mole, so minus C1, and your temperature changes T1 minus TF, okay, let's say T1 to TF, okay, and the minus signs, which is equals to, and this one is plus sign, C2 T2 minus TF, okay, the final temperature is TF, right? So since the total energy of the combined system is conserved, so that means delta Q is same, okay, and heat released from the first systems Okay, so T1 minus Tf and then minus C1, and other one is the plus C2 equals times T2 minus Tf. So ordering is the same. So therefore the T2 is equals to C1 over C2, T1 Tf minus T1 plus Tf, right? So very simple, right? So this is the answer. Okay, so basically balance the delta Q. Okay, since the total energy of the combined system is constant. Okay, so let me stop here. So we meet tomorrow. Okay, and tomorrow I will solve assignment 12 problems. Okay, and also if time permits, I will solve some extra problems. Okay, that is related to the black body radiations. Okay, so then see you tomorrow.